Can everyone hear me? Okay, so I think everyone can see my screen. Hi everyone, thanks for coming, and I'm Ju-young, and today I'll be talking about quantum computation by adiabatic evolution. This is a paper uploaded onto arXiv in the year 2000. It's a bit of an old paper, but I think that it gives a nice introduction to this field. And today I would like to give a short introduction, followed by talking about how we can use adiabatic evolution for solving satisfiability problems, and then give some nice examples, and then talk about the relationship between the conventional quantum computing paradigm with the adiabatic evolution, and then wrap up with a short summary. So as an introduction, I would like to talk about what types of problems we're trying to solve and how we propose to solve them. So last week, Xion gave us a nice introduction about one-way quantum computing. And so I decided that maybe this week it would be nice to talk about another type of quantum computing. And the type of problem that we're trying to solve today is something called the satisfiability problem. So let's say that we have n bits, and each bit can be either 0 or 1. And we have many different clauses, and these clauses can be true or false given the value of some of the n bits. So depending on the combination of the values of the bits, then the clauses can be either true or false. And we want to solve a problem where many of these clauses are all satisfied. So let's try to solve this by minimizing some energy function. And we can construct some time-dependent Hamiltonian with m terms, and each term is corresponding to some clause. And we want to make this Hamiltonian so that the ground state at time t is equal to large T encodes the solution. And we call this adiabatic quantum computing, where we try to use the adiabatic theorem to prepare this ground state of the final Hamiltonian. Then we can measure this state in order to find the solution to our problem. So this is the basic overview of what we're trying to discuss today. And next, let's talk about what is adiabatic evolution and how can we use this to solve the previously mentioned satisfiability problems. So before talking about the adiabatic theorem, I would like to talk about the Schrödinger equation. And this equation describes how the quantum state changes over time. And we can see that this change is determined by the Hamiltonian. And let's write this Hamiltonian in the following way. So let's write the Hamiltonian ht as h tilde s, where s is a value between 0 and 1. And here we parameterize s by t over large T. So basically, this large T determines how long this evolution will take. And for each s value, we will have, for each instance, we can have some energy eigenvalues and energy eigenstates. And here, this L value basically tells us the spectrum. So E0s will be the ground state, and E1s will be the first excited state. And then we have the adiabatic theorem. This is pretty long, but I'll try to explain it very shortly. If the initial state is the ground state of the initial Hamiltonian, and if t is larger than some value, then the state at time large T will be arbitrarily close to the ground state of the final Hamiltonian. And here, these values are as follows. So G min is the minimum difference between the first excited energy and the ground state energy at time s. And here, this E is the maximum value of this value. So basically what this tells us is that if we start from the ground state of our starting Hamiltonian, and if we vary the Hamiltonian very slowly, determined by these two values, then the final state will be the ground state. So this is important because, as discussed before, the way that we're trying to solve the satisfiability problem is we're trying to encode this into the ground, encode the solution into the ground state of the Hamiltonian. So in this way, we will be able to prepare a ground state of some Hamiltonian by changing the Hamiltonian very slowly. So let's give a simple example of how we can construct such a Hamiltonian. So let's consider a 3-sat problem. So this has Boolean clauses, and each of them is affected by 3 bits. So we can define an energy function for each clause. And let's say that for this clause C, it is affected by the bits ZIC, ZJC, and ZKC. So these are each bits. They can be either 0 or 1. And this energy value is 0 if C is satisfied, and 1 if C is not satisfied. So we can see that if we sum over all of the clauses, then this large energy function, the sum of the energy functions will be at ground state if all of the clauses are satisfied. And so we can use this to create something called the problem Hamiltonian or the final Hamiltonian. So this Hamiltonian has the ground state as the solution that we're trying to find. And we define a Hamiltonian term for each clause. And this Z1 state is basically a 0 state or a 1 state, depending on the value of Z1. And this Z1 through Zn is written like this is the product state of each qubit. So we create a Hamiltonian for each clause so that the eigenvalues are the energy function values. And then we can sum over all of the clauses to create the problem Hamiltonian. And we can see that the ground state of this Hamiltonian will have our solution. And if we measure the final state in the basis of the computational basis, then we will be able to know our solution. For the initial Hamiltonian, we want some Hamiltonian where the ground state is easily prepared. And in this case, we choose this type of initial Hamiltonian, where the ground state is some superposition of all of the possible bit strings. So basically, we have an evolution from the initial Hamiltonian to the final Hamiltonian. And in this paper, they decided to choose this type of evolution. So basically, we linearly change from HB to HP. And we can write this in terms of S as follows. And since we can write each of the HP and HB as a sum of some Hamiltonian terms on each clause, then we can write the entire Hamiltonian as a sum of Hamiltonians for each clause. So this is one example of how we can construct a Hamiltonian in order to use the adiabatic evolution to our advantage. So when can we do this? We want to be able to get the ground state of the final Hamiltonian in a relatively fast time. So we want T, large T, to increase polynomially with the bit number. If it increases exponentially, then if the problem size becomes too large, then we won't be able to calculate it in a reasonable time. So let's think about what affects T. So if we consider the if we consider the condition for the adiabatic evolution, then we can see that large T is determined by E and G min. And actually this E value is only increases polynomially with N because we assume that the number of clauses only increases polynomially with N, and that E is upper bounded by the maximum of some eigenvalues of the Hamiltonian HP minus HB. And so this means that basically E is upper bounded. So we can see that G min controls T. And we want G min to be order of some inverse of a polynomial of N. So in this case, we can say that our formulation is tractable. So to give a short summary of what we discussed so far, let's say that we are given a satisfiability problem and we want to solve this using AQC. Then we construct HB, which has a ground state that is easily prepared, and HP, which has a ground state that encodes the solution. And we find some way to evolve it from HB to HP. And if we have some method, then we can find the sufficient evolution time, large T, which is determined by E and G min. And then we can prepare the initial state and then evolve it using HT for time large T. And then we can measure the final state to get our solution. And this is basically the way that we can do quantum computing using the adiabatic evolution. And so since we have some idea of how to solve some problems, let's actually try to solve some problems. So there's many examples given in the paper, and I would like to only introduce two today. The first one is a toy problem, and the second one is the Grover problem. So let's consider a 1-qubit toy problem. And this toy problem has only one clause and 1 bit. So the clause is satisfied if and only if the bit is 1. So let's try to construct the Hamiltonians that are needed. For the problem Hamiltonian, we can write it as 1/2 the identity plus the Pauli Z operator. And for some of you who don't know what the are not familiar with the Pauli Z operator, it has the eigenstates of 1 state and 0 state, and the eigenvalues are as follows. So we can see that when the ground state of HP is the 1 state, and we construct the initial Hamiltonian as follows. Then we can create this H tilde S and then solve the eigenvalue problem. And then we can see that the eigenenergies are as follows. And if we plot that on a graph like as follows, we can see that the G min is at S is equal to 0.5, and that actually it's pretty large. So we can see that G min is not 0. But let's say that we change our formulation so that the initial Hamiltonian is written as follows. Actually, instead of using the X Pauli, we use the Z Pauli. Then we can see that actually the H tilde S eigenvalues has S and 1 minus S. So at S is equal to 0.5, that G min is actually 0. So we will not be able to use adiabatic quantum computing in this. Can everyone hear me? Okay. So I'll begin where we left off. So we were trying to solve one qubit toy problem, and we had one clause and 1 qubit, and we wanted that qubit to be 1 state. And we gave 2 constructions, and one had the initial state that in the basis that is not the computational basis, and one had the same basis as the our target solution state. And we saw that for one case, the G min was not 0, and so AQC is possible. And for one of them, the G min is 0, so AQC is not possible. So I would like to move on to the next problem, which is the Grover problem. So we have one clause again, except that this time we want this clause is satisfied when our bit string is exactly one of the possible bit strings. So here, this bit string W is unknown, but we have access to a Hamiltonian that tells us whether or not the bit string is the one that we're trying to find. So basically, we have access to an oracle. And so classically, this is basically trying to search in an unstructured database. So the way to solve this classically is just test 1 by 1. And so if we have 2 to the n power number of items, then on average, we will need 2 to the n power divided by 2. queries to find the W that we're trying to find. So the Hamiltonian that we have is written as follows. So the eigenvalue is 1 when z is 0. Z is exactly not the when z is W, we have the 0 state, but sorry, I'll start over again. So for the problem Hamiltonian, we have eigenvalue 0 when z is equal to the state that we're trying to find. And we have the z state when z is not the state that we're trying to find. So it's written as follows. And we can see that the ground state is when z state is W state. And we have the initial Hamiltonian as follows. And this is the same one that we were using in the previous slide. And in the paper, they give some nice algebra, and it's actually quite long, but at the end, we can see that G min is about this value, which means that T is much larger than 2 to the n power. So basically, there is no quantum advantage. And as before, I explained that if we have 2 to the n power of items, then on average, we would need 2 to the n minus 1 power queries. So there is no advantage here. But the interesting thing is that I think that some of you will know that for the gate-based quantum computing, for the Grover problem, we have some quadratic advantage. So instead of 2 to the n power, if we use gate-based quantum computing, we can use the square root of this value. And so can we actually do that with adiabatic quantum computing is the important question. And it was not talked about in the paper, but as a side note, I would like to discuss about this. And so the picture on the left shows the 2 lowest eigenvalues of the previous slide's formulation of the Grover problem. And I would like to discuss what we can observe from this picture over here with you guys. So the first question is, let's compare the eigenvalue difference at different S values. So this is the minimum. And for the other values, the difference is much larger. We can see that. So we can see that this is the defining step, the defining minimum value that controls the entire evolution. Then I would like to ask you guys as an open question, how can we use this observation for faster calculation? Does anyone have an idea of how we can use this? Okay. Is there chat? Yes, thank you, Yeojun. So he wrote in the chat that we can evolve faster when the gap is large. So basically, the rate that we were changing from the initial Hamiltonian to the final Hamiltonian was determined by just this, by the S near here. When in fact, when S is smaller or larger, we have a much larger gap. So we can change faster during this phase and this part, and change slowly here. So this is the basic idea behind local adiabatic evolution. So basically, instead of using the adiabatic condition on the entire evolution, we apply this condition to a very minuscule time step for each S. So by doing this, a paper that was published in 2002 showed us that we can get the quadratic speed up, just like the gate-based methods for the Grover problem. So if anyone's interested, I would like to suggest this paper. And it goes into much more detail about how we can change the S to get a better computation time. Okay, so let's move on. And as another side note, this paper also talks about trying to find some problem features that determines large T. So since solving the eigenvalue problem is pretty difficult, maybe we might be able to find some interesting features that tells us something about large T. And so they compared 3 problems. So for this problem, we can see that G-min is a polynomial in n, so this is nice. And that the degeneracy of the first excited state is about n squared. And that for the Grover problem, we have some exponential here, and we have some exponential here. So maybe with just these 2 examples, we might think that the number of degeneracy of the first excited state is important, but they gave some counterexample where G-min is a polynomial, but the degeneracy is actually exponential. So we can't judge the size of the minimum gap with the knowledge of just the first level degeneracy. So this paper concluded that it was actually pretty difficult to find some problem features that determines large T. Okay, then I would like to move on to how we can represent AQC as some gate-based quantum computing. So when I say gate-based quantum computing or the conventional quantum computing paradigm, I mean that we express the computation as some product of many unitaries, and these unitaries are acting on some small subset of the qubits. So to show the relationship, the paper uses time discretization and trotterization. And there's a lot of maths here, and I don't want to go into much detail, but to just talk about the main ideas about their proof. So actually, the time evolution of a quantum state can be written with a unitary transform. And so if we have some transform from time 0 to large T, then we can discretize the time by this delta. And then we can write each of these discretized unitaries as follows if some condition is satisfied. And then we can use something called a trotterization to write it in terms of multiples of HB and HP. And because of the properties of HB and HP, mainly that the number of clauses is only polynomial in the problem size, we can show that this UT, 0 is well approximated by a product of unitaries on only a few qubits. So basically, we can write AQC as gate-based quantum computing. And so this is the big idea behind the proof. And I think that the main important thing that we want to take away from this is that AQC can be written with gate-based quantum computing, and we can prove this using these 2 main ideas. And to give a short summary of what we talked about, so I introduced something called adiabatic quantum computing. So at time 0, we have a Hamiltonian, and we have a ground state of this Hamiltonian. And the condition here is that this state should be easily prepared. And then we change this Hamiltonian slowly by some schedule determined by G-min, the minimum difference between the eigenvalues of the first and ground state, first excited and ground state. And then at time large T, we have some final Hamiltonian, and the ground state of this final Hamiltonian encodes our solution. So by measuring this state, we can get our solution. And with this process, we can find some answer to our problem. And in general, we don't know the required running time without calculating the G-min and the E value. And AQC is well approximated with a product of many unitary operators, each acting on only a few qubits. And so this paper was written maybe at the start of this field. And since then, there has been lots of research on how to improve this and how to apply this to many different problems. And for anyone who is more interested in this subject, I would like to suggest reading this review paper written in 2018. It goes into much more detail and gives nice examples of problems. And so thank you for your attention. If there's any questions, please use the mic or the chatting board.
Okay, that was an interesting presentation. Thanks. What I want to ask you about is like the complexity of adiabatic quantum algorithms. Yeah, it has been always confusing for me, like determining the complexity. So, if I'm not wrong, we determine the complexity by the energy difference between the lower two eigenstates, right? Two energy states. Like we want it to be slow enough not to mix up those states, right? But I saw you that you kind of related it with the size of the problem in the previous slide. But like, yeah, like how do you relate the size of the problem with the complexity? I mean, like, how do you determine the complexity of the problem? Maybe while you're trying to determine epsilon and G min. There was one slide, I guess.
This one or this one?
And not this one. Like when you're determining the complexity for the while like there was a slide you were talking about epsilon and G min. Yeah, maybe here.
Maybe here.
Yeah,
Okay.
yeah. I think like you determine. You kind of. You say that it runs in polynomial time, right? The whole algorithms. So, like, but as far as you discussed, like the complexity, we determine the value of t by the energy difference between the two lower energy states, right? But
right.
How do you relate it with the size of the problem?
So actually, if you solve the energy value, I'm sorry, the eigenvalue problem, it naturally just comes up.
Okay. So it's like it's kind of it's related with the size of problem when you determine the value of epsilon, right? But G min is not related with the size of the problem, right?
It okay. So E is definitely related, and I'm kind of confused right now. But I think that there can be cases where G min is affected.
So does it mean that okay, yeah, go ahead.
Yeah, so can I come back to this question? I think that there's something that I can
sure.
show you.
Okay, sure.
Wait just a moment.
Yeah, most of the time, like we consider it
Okay, so this was actually something that I wrote for a class, but this is exactly the Grover problem, and yeah, this is the global evolution that I showed you in the presentation. And if you solve the eigen problem, actually, interestingly, we get eigenvalues that have some dependency on the number of bits. So yeah, actually, the eigenvalues are affected by the problem size.
Okay.
So there's some cases like this. Okay.
So now it's okay. I think I see it.
Yeah.
So like in general, does this kind of formulation happens for all adiabatic quantum algorithms? I mean, can we always relate size of the problem with the complexity?
So I guess it
Or
would
is it
depend
a
on
special case? Okay.
So like the toy problem I showed you didn't have any like size scaling because the problem itself was defined just on the one qubit. But I guess if you have a problem that can scale, then the time should be affected by the scale. Because like if you think about a case where you can change the scale of the problem, but the time is not affected by it, then that somehow intuitively doesn't make sense.
Yeah. Okay.
Yeah.
I think you answered my question well.
Okay.
Thank you.
Thank you. Is there any other questions?
Okay. Thank you for your presentation. And can I ask a question? Okay. So, in global algorithm and also AQC, we assume that we already know the solution, and we use that solution state to construct a problem Hamiltonian, right?
Okay, so I'm kind of confused by this too, but I think that we don't know the solution. We just have access to this Hamiltonian.
So that's a assumption, I guess. Like we can in global algorithm, we assume we can construct oracle, right?
Yeah, it's basically I think the same thing. So same as you said in the Grover algorithm, we have access to some like gate that tells us if whether or not the input is the one that we want, right? So it's the same thing here. We have a Hamiltonian that has the ground state that is the solution that we want. Yeah, so actually I was very confused by this too. And I'm kind of still confused by it, but I think that if we think about it this way, then there is no, then we can say that we don't know the solution when we're making this problem.
I was like imagining something like some real physical Hamiltonian that is given, but we don't know the eigenvalues of it. So we can solve that eigenvalue problem with AQC, maybe.
I guess that's a very nice way to think about it. Like where a situation where all of the other energy has eigenstates have just the same energy, and the one has just higher or lower eigenvalue. Maybe that would be the case that we're trying to solve here. Thank you for the good insight.
Okay, actually, I have another question. What would happen if you have multiple solutions?
So I know that the paper that sorry, I'll share the presentation again. So I think that, oops. Yeah, I think that this paper goes into more detail about this case. And actually, I'm not very familiar with how they deal with it, but I think that you can still do the same thing and get eventually the results that you want.
Okay, thank you.
One more question. We also need to do some sort of sampling, right? It's not one-time evolution.
Right.
So like, does that also affect maybe that could also be taken into consideration while we're trying to solve the problem with this kind of adiabatic quantum algorithm?
So I think that actually we assume that we have T that's large enough so that we have almost probably the
Okay.
solution. So
so we have higher probability, so we kind of design it in a way we don't need to repeat the experiment so many times, right?
yeah, I think so. So I think maybe I actually don't precisely know, but maybe that's the difference between adiabatic quantum computing and annealing. So annealing has more cases where so annealing has a high probability of the solution, and adiabatic quantum computing has almost exactly one probability.
Okay. Thank you.
Yeah, and yeah, thank you for your very practical question.
Okay, so could you tell us about the difference between annealing and adiabatic process?
So so as far as I know, the way I understand it is that annealing is kind of like adiabatic computing, except that we allow for faster evolution in with trade-off for the accuracy. So basically, we have much higher probability to measure other states that rather than the solution state, but we allow for other types of evolution other than adiabatic evolution. So yeah, that's kind of how I understand it. But yeah, I have very limited scope about this field, so I think that that's about as far as accurate as I can get. Okay, so Kim Min-soo asked if we evolve Hamiltonian adiabatically, then can't there be some effect of dynamic phase or geometric phase? And shouldn't we take account of this? So I'm sorry, but I don't have a good understanding about what dynamic or geometric phase is. So can you give a bit more explanation about dynamic phase or geometric phase? Okay, so he says that this type of phase is something like exponential of I times ET. So I'm guessing that this is multiplied to, is this like a global phase or so? I'm not quite sure, but as long as the measurement probability is same, I think that it will not cause too much problem. So the way that we understand, the way that we just get the solution is measuring in the basis, measuring in the computational basis, in the Z basis. So if it's global phase, then I don't think that there will be too much of a, I don't think that there will be an effect. So he asked that, does that mean that Z since all we are looking at is the expectation value, there is no effect of the phase. And yeah, I think so. Thank you.
Can I actually ask question to Sukim? Would that be okay, Minsu? Okay, so the as you said, dynamic phase or geometric phase is kind of a global phase. Then, well, I don't know much about this field either, but we can't really observe global phase. So, how can we use this dynamic phase or geometric phase in a practical way? Do you have any? Is there any research on using dynamic phase? So in order to do that kind of experiment, okay, so instead, when when two systems have different phase, there'll be some interference, which is physically observable. So if you want to do that kind of experiment, we need to evolve one system in adiabatic process and other. So we have to evolve two systems in different adiabatic process. That's related with magnetic phase, right? Magnetic flux. Yeah. Okay. So do you guys have any other questions?
Yeah, can I ask one question? And can you guys hear me?
Yes.
So, Shihan asked about the difference between quantum annealing and AQC. And as far as I know, quantum annealing is not universal, whereas adiabatic quantum computing is universal. But according to, as far as I understand, what Zhuyang said was that there's more option for the quantum annealing because you can choose whether to have the Hamiltonian evolution like fast, like quickly or slowly. So, but as far as I know, quantum annealing is not universal. So could you do you know why quantum annealing is not universal, whereas adiabatic quantum computing is universal?
Okay, thank you for the question. I don't know if I'll be able to answer this accurately. So maybe it's best for me to not comment too much about this, but so maybe one thing that we can consider is that if we look at this adiabatic theorem here, if we have, so let's say that we're trying to evolve one state to another state, then we can set initial Hamiltonian that has a ground state, that is the initial state, and then we can set a final Hamiltonian that is the that has the ground state as our objective state. Then we will be able to do some adiabatic computing. So maybe in that sense, we will be able to do that. We can say that adiabatic quantum computing is universal because we can change one state, any one state from one to another state. But for annealing, so I'm not comfortable commenting on this, but maybe since we don't have exact control over the states, then maybe we can't prepare the final state arbitrarily accurately. So that will that may mean that it is not universal. But I don't know about the universality of AQC or annealing. So I think that's my speculation on this subject.
That's great. Thank you for the answer.
Thank you.
Okay, so if you guys don't have any more questions, let's end this presentation here. And thank you for your wonderful presentation, Jiyoung. So Minsu commented on chat board and so yeah, Minsu, you mean like current in Sweden? Okay. So when you say when you say current, you mean the current in like superconductor? Hmm. Okay. Thank you for your comment. And so if you guys don't have any other questions, let's end this meeting. And thank you for your presentation, Jiyoung. And there is one notice. So we need to check attendance every week. So it would be grateful if you guys prepare your mics and cameras. It would be grateful. And when you ask questions, since I'm uploading all the videos to YouTube, I have to manually type the comments in chatting board. So you'd be grateful to ask questions in using your microphone. That'd be great. Okay, that's all for today. And next week is Ho-Jun will present, right? Is Ho-Jun here? Okay, so Ho-Jun will present for us, and have a nice weekend and have a nice Lunar New Year. Thank you.